Hello, this lecture is about identifying the types of structures and classifications of buildings. This is an important first step in the design of a structure because the loads and the design parameters for the structures can be quite different for structures that are built in different ways or are built for different purposes. Let's get started. We'll start off by describing the process of design. The design process consists of several steps, from conceptualization to planning through design and culminating in construction of the selected alternative. Conceptualization is basically the brainstorming stage of the process where several different ideas are considered, but none are developed. Next, the planning phase involves further developing some of the ideas from the conceptualization phase of the project using sketches and models. After that comes the design phase, where one or two alternatives are developed to the level of selecting structural configurations and preliminary member sizes. Finally, one of the alternatives is selected for construction, resulting in the construction of the structure. Depending on the particulars of the project, most of the work for the engineer takes place during the third step. A structure's primary purpose is to support the building that it is a part of and to transmit all the imposed loads safely to the foundation and to the ground. You are all familiar with the fundamentals of structural analysis, which is the determination of member forces and deflections in the structure. This is the first class that deals with structural design, which involves arrangement and sizing of members in the structure so that it is able to perform its intended function. Structural engineering is the iterative process of analyzing and designing a structure. The main focus of this class is to determine the loads that the structure is designed for and to look at different options for the structural systems. The first step is to discuss different types of structures and the classification of those structures. A structural system can be defined as a deformable assemblage of various types of structural members that is designed to carry loads to the ground. The most common types of structures, such as buildings and bridges, are typically built from discrete members, such as slabs, beams, columns, cables, arches, etc. Alternatively, structures may be made of structural assemblies, such as trusses or frames, which themselves are made up of discrete members. Structures may also be made from continuous surface elements, such as shells or membranes. Structures can be classified in many different ways, depending on the objective. All structures are built to serve specific functions. Consequently, structures are often classified according to their functions or the purposes they are intended to serve. They can also be classified by visual appearance. Structures can broadly be classified as building structures or non-building structures. A building is a structure that is designed essentially for residential, commercial, or industrial purposes, and also allows for structures that are designed for institutional purposes, public assembly, or for multiple uses. Bridges are the most common example of non-building structures, and they are found on highways, railroads, in parks, etc. Other civil engineering structures include industrial structures, underground structures, and hydraulic structures like weirs and dams. And in a broader context, automobiles, railroad cars, airplanes, cranes, transmission towers are also called structures, but are often designed by mechanical or aerospace engineers. Okay, buildings can be classified based on a number of different attributes, and some of those are shown here. Some of the common attributes that buildings are classified based on include the form of the structure, the material from which they're constructed, the load path that is employed in the structure, the method by which they are analyzed, the methods by which they are designed, the use and the occupancy, or the height of the structure. Structures can be classified into two broad categories based on their structural form, either a framed structure or a shell-type structure. Frame structures include conventional structures that are characterized by assemblies of elongated members such as beams, girders, columns, trusses, rigid frames, or three-dimensional frame structures. This is a picture of the new CBA building out in front of the ERC on campus. Shell structures are made largely from plates or shells, which are used both as functional coverings and as main load-carrying elements. This is a picture of the Sydney Opera House, and the roof, or the characteristic form of this structure is a shell type of element. Buildings are often classified by the material that's used in their construction as well. Common building materials include steel, reinforced concrete, pre-stressed concrete, masonry, which includes brick and cement blocks, and wood. Materials are also broadly characterized as either combustible or non-combustible. The definitions are fairly straightforward. Non-combustible materials are those that won't catch on fire when subjected to heat or flame. Type 1 and Type 2 construction generally means that the materials are non-combustible, and this includes steel, concrete, and masonry elements. Combustible materials are those that do not meet the definition and requirements of non-combustible materials. Types 3, 4, and 5 construction are construction types that are generally made out of combustible materials, and this basically means wood construction. Now, the different types, 3, 4, and 5, correspond to the different types of wood members that are used. So one type might correspond to lighter members like 2x4s, whereas another type might correspond to heavier timber type members that might be 8 inches wide and 24 inches deep, for example. One of those is going to burn much faster than the other. Okay, now for a bit of trivia. Question. The origins of the current building codes can be traced to what events? Okay, 3, 2, 1. The answer is the Great Fires that swept through the United States cities in the 19th century. Believe it or not, the origins of the building codes go back to the Great Fires in the 1800s. In 1838, there was a fire in Charleston, South Carolina, that destroyed about 1,000 buildings. There was one in New York City in 45. There was another in Pittsburgh in 1845. The San Francisco fire in 1851, and then the Great Chicago Fire in 1871 was really the event that really defined building codes. Okay, it was the largest. I'm sorry, Chicago was the fifth largest city at the time, and in the fire started when Mrs. O'Leary's cow knocked over a kerosene lamp, or another version of the story goes that there were some drunk men that were gambling and knocked over the lamp instead. But anyways, the fire burned for roughly 24 hours and only stopped because it burned itself out, ran out of fuel, and because it started to rain. So 1/3 of the city was destroyed, including 2,000 acres of property. 17,500 buildings were destroyed. 300 people were killed, and about 100,000 were left homeless. The financial losses were also staggering: $222 million in property damages at the time, which would correspond to almost $5 billion in today's money. So the pictures on this slide obviously are old; they come from the 1800s, but the shows the devastation in the city after the fire. You can just see that most of the buildings were turned to rubble. Okay. If it wasn't bad enough that it happened in 1871, it happened again in 1874. They call it the Little Chicago Fire. In this case, only 47 acres of property were destroyed, only 812 buildings were burned, and only 20 people were killed, thus making it the Little Chicago Fire. That would be a devastating event by itself, but when it compares to the fire in 1871, it really wasn't as large. As a result of these, in 1875, Chicago codified the regulations corresponding to buildings and created a Department of Buildings to administer that code. Chicago was rebuilt again to become the fourth largest city by 1880, which is quite a feat. They embraced the idea of steel construction. The Home Fire Insurance Company building was one of the first steel buildings in the United States. And with this building, it has a steel core and has a masonry or stone outside facade. So therefore, it became the first all-steel skyscraper in the United States, built in 1885. All right. So another way of classifying structures is based on the load path. Consider this truss shown on this slide, and let's subject it to a point load in the middle panel point, acting downwards like this. And where is the load path for this structure? So if we were to trace the load from its point of application to its foundations, it basically comes up through this member here as a tension. It goes up through this member here as a tension, and then it acts in compression down through these end posts like that and finds its way to the foundation. Now, you guys all know from statics and analysis that if we have a tension coming in through this diagonal member, that there also has to be compression at this force in order to provide equilibrium. There has to be tension in this member down here in order to, whoops, I drew it as compression. There has to be tension in this member down here in order to counteract the compression up here. There has to be compression at this node and this node. There has to be tension down here. But primarily, the load path that is being employed goes through these members like this, and then the other members are there to provide equilibrium. So the question is, what happens when we have a situation where one of these members breaks? Let's suppose that this diagonal member fractures. What happens to this? Well, it actually fails. Why? Because there's only one load path that works for this structure. And if we lose one of those members, then the structure is no longer stable. So this type of a structure is called non-redundant because there is no secondary load path in the event of the failure of one of the members in the primary load path. So as a contrary example, version of the truss. Same truss, but I've added some members to it. So where's the load path in this structure? Well, it's not entirely obvious, but part of the load keeps going the same way that it did through this diagonal here, through that diagonal there. But now there's an extra load path, and I'll draw this in using a different color. Let's suppose I'll use orange. Some load can be carried by that member now. It goes up into this node at the top, and then these members are carrying in compression. So there's a secondary load path that's present in this truss that wasn't present in the earlier version, where if fractures, there's a second load path that's still there to carry that load and keep the structure stable. Okay, like this, then this member would go into compression, and this member here would go into tension like this, and then this member here would go into compression again. So secondary load path. Okay, so we can classify structures based on their redundancy, whether they're redundant or non-redundant. So based on load path characteristics, structures can be classified as either redundant or non-redundant structures. A redundant structure is one in which the collapse of one of the structure's members would not lead to a collapse of the entire structure. So from this point of view, you could think of structural redundancy as insurance for the structure. You might also think of it as a belt and suspenders approach to designing. If in the event of the failure of one member, there's another one to carry the load. A non-redundant structure is one in which the collapse or failure of one of the members results in the collapse of the whole structure or at least part of the structure. This type of structure is sometimes referred to as fracture critical. Okay, this is a bridge in southwestern Pennsylvania outside the town of Katanning. It's over the Allegheny River before it forms the Ohio River in Pittsburgh. And it's a classic truss bridge. If we zoom in on one of the spans, this is the longest span of the bridge. And it's a span over the navigable channel in the river. There's a lock and dam system just upstream from this bridge. So this is the navigable channel. So this particular truss is statically determinate, meaning that the equations of statics can be used to solve for the member forces. But one of the characteristics of that is that with this particular bridge, if you lose any one of these members, that means that the structure is going to collapse. So if you end up with a failure of that member right there, for instance, that means that the structure is probably going to collapse and fall into the river. Thus, this particular truss is non-redundant. Consider this bridge instead. This is a more modern cable stay bridge outside of Portsmouth, Ohio. And this is called the U.S. Grant Bridge. So with this cable stay bridge, It has a much more redundant system. So if you were to look at the distribution of the load path in this bridge, then a truckload here, the load goes up through this cable, down into this tower, and then into the foundation. Or if you put the truckload over here, it goes up through that cable, down through the tower, and into the foundation. So the difference is that if you lose one of these cables, if you were to lose one of these tendons there, that there's an alternative load path for the load to go through to reach the foundations. So this is a more redundant structure. Therefore, it's considered by just about everybody to be a safer structure. And it means that the failure of just one of those tendons will not likely lead to the collapse of the structure. In fact, when they design these cable stay bridges, they design them so that the cables can be removed one at a time in case they need to be replaced. Okay, talking about load paths, there's also a classification of structures based on the load path that the structure is employing. So in this case, this is a couple of gravity systems, so gravity loads pointing down towards Earth. The one on the left is a bearing wall system, so the gravity loads are carried from the roof and the floors in through the walls and then down into the foundations. Whereas over on the right, you see a structural steel frame system, where in this case, if you apply a load to the floor, the load has to go from the floor decking to a floor beam, from the floor beam into a girder, from the girder into the column, and then from the column down into the foundation. Okay, there are similar arrangements for concrete buildings as well. The system on the left is a concrete system using a waffle slab or a one-way beam system. The concrete system on the right is using a flat slab system. There aren't any beams in that system. But in either case, the load goes from the floor into the columns and then down into the foundation. So these are two examples of gravity systems. And then the shown on this slide is more of a residential kind of a system where the load would go from the roof or from the floors in through the walls. And unlike the bearing wall system where the wall itself is solid, in this case, the wall is made up of 2x4s or 2x6s in some cases, and that framing carries the gravity loads into the foundation. So alternatively to gravity, lateral loads. So when the wind blows horizontally and acts on a structure, or when an earthquake occurs and causes a seismic excitation of the building, then we have to carry the lateral loads to the ground as well. In the case on the left is a moment frame. So we use frame action in the system in order to carry the lateral loads to the foundation. The system in the center is a brace frame system where the bracing members carry the loads, much like the truss action that we saw before. So if you see a lateral load acting like that, that would be carried in compression there and in tension there, and then it would find its way down through the bracing system to the foundation. And then the system on the right is a shear wall system where these walls here act in shear to carry the lateral loads to the foundation. So we put a lateral load on it like that. You end up with a state of shear acting on that slab that's arranged vertically all the way down through to the foundation. Okay, structures are also sometimes classified based on how they are analyzed. Analysis could be a linear or a nonlinear type of analysis with respect to either material or geometry. So with material, if you assume that it doesn't yield and behaves linearly, that's one option, or you could assume that the material yields or fractures, that's another. If we look at geometric nonlinearities, you could assume that the geometry changes while the structure is being loaded. We all know that structures deform. Whether you account for that deformation during the analysis or not defines whether you're dealing with geometric nonlinearities. You can characterize structures as one-dimensional, two-dimensional, or three-dimensional, and you might also apply assumptions to the analysis based on whether you think the structure is going to behave like a truss, like a beam, or like a frame. And you also have different analysis techniques for brace frame system versus moment frame systems. or whether the system could be analyzed as a plate or a shell, as a cable in some cases, or as a membrane structure in even fewer cases. Okay, there's also characterization based on the design assumptions or the design methods that are made in a structure. This comes from I think this is the one slide that alludes to design overseas. In the UK, they characterize the type of design method as small static structures, or Class a large static structure, Class C, a structure that is characterized based on its dynamic performance, Class D, or an aeroelastic structure, Class E. So the overwhelming majority of structures belong to the Class A. They're just small static structures, and that's certainly true in the United States as well. All right, in the US, the method of design tends to revolve around the predominant effect that's driving the design. So if you're on the West Coast, you could be dealing with seismic framing. We classify that as either low seismic or high seismic. If you're in the Midwest, for instance, in the Ohio area, then most of the design is probably non-seismic. Wind might govern in areas around the coast, say Florida, for instance, where you have high hurricane winds, or even in the Boston area where you might get nor'easters and things like that. In other cases, the gravity load is going to define the type of framing that you use. So, three different classifications based on the type of framing that is driving the design selections in the building. Okay. Buildings are also classified based on the use category. As the risk of human life in the unlikely event of a structural collapse increases, the code requirements for design become more stringent. We have classification for the buildings called use categories, and they include essential facilities, hazardous facilities, standard occupancy structures, special occupancy structures, or miscellaneous structures. And then we have some structures that are intended for two or more uses, and they are called mixed occupancy type structures. So when we look at the classification, we go to International Building Code Section 302, or there's an analogous section in the ASCE specification as well. But basically, these different classifications are classified as numbers 1 through 10, where you have buildings that are intended for assembly, for business, for education, for factory or industrial use, for high hazards, institutionals like prisons and things of that nature, mercantile, residential structures, storage structures, and then miscellaneous groups. Now, determining the classifications isn't as simple as just looking at these 10 things. If you look at the code itself, it's very involved and gives very specific criteria that has to be met for each one of these different uses or occupation classifications. But getting into the details of that is not really in the scope of the class. This is something you'll have to determine as part of your design group when you get out into practice. The leader of your design group, your mentor, will probably play a larger role in determining specifically which occupancy is governing for which particular type of building. Some general concepts regarding occupancy type, though. The first are essential facilities. These are buildings and structures that would be necessary to the community to respond to a natural disaster or some type of emergency situation. So you want to be thinking about hospitals, police stations, fire stations, communication centers, things of that nature. So the idea is that if there's an earthquake in an area, firemen are going to need to respond, so they wouldn't want the fire halls to all collapse during the earthquake. Ambulances are going to take people to hospitals, so you want to make sure that the hospitals are in service immediately after the earthquake. So when we design these types of structures, they have different design criteria. Another consideration are hazardous facilities. These are buildings that or structures that whose failure would cause some type of ill effect to the community around it. So think about a nuclear power plant. So if there's an earthquake or a tsunami, for example, and a nuclear power plant releases radiation into the atmosphere, that would be bad. So they're designed to a higher standard, a different standard. Chemical plants, things of that nature, hazardous waste facilities are all designed to a special criteria. Another consideration would be special occupancy facilities, basically arenas and things that are where a large number of people are going to congregate. So, um, arenas, theaters, lecture halls, things of that nature, basically where um, people are going to be congregated in one area and they're not going to be able to leave in a quick way. And then finally, we have additional criteria for buildings subjected to wind and seismic. Certainly, we have wind everywhere, and there's a potential for seismic everywhere. But there are parts of the U.S. and parts of the world where these actions are going to drive the design of the structure. And in those cases, we have different design criteria for those buildings. With that being said, risk categories are assigned based on the occupancy and the use of the building. There's 4 of them, 1, 2, 3, and 4. Buildings with a low risk are assigned category 1. Hazardous facilities are assigned to a category 3. Essential facilities are assigned to a category 4, and everything else, which includes typical office type buildings, are assigned to a category 2. Okay, after the risk category has been assigned, the importance factors are then determined using the table shown in this slide. In general, the forces that a structure are designed for are multiplied by this importance factor. Thus, when designing for seismic, an essential facility, like a hospital, for example, would be designed for 50% larger forces than a typical building, like an office building. Okay, the image on this slide illustrates the basis that's used in determining risk categories for structural design. That is based primarily on the number of persons whose lives would be endangered or whose welfare would be affected in the event of a failure. So if we're talking about a grain silo or a storage building or something like that, it's going to be a risk category 1 type of a structure because the risk to human life is relatively low. Whereas when we're looking at a hazardous facility or an essential facility, the number of people that would be affected by its failure is much, much higher. Okay, the last type of classification that we'll discuss is a classification based on height. From a design perspective, buildings are classified as low-rise, mid-rise, or a high-rise. A low-rise building is defined as one in which the design of the structure is predominantly governed by gravity loads or vertical loads. Although lateral loads, such as those induced by wind and earthquake, can't be ignored, they have little or no effect in sizing the members of a low-rise building. Houses, hotels, motels, dormitories, and low-rise apartment buildings are examples. Other examples include most office buildings, educational facilities, hospitals, medical facilities, and things of that nature. Okay, the second category is a high-rise building, and this is one where the design of the structure is governed predominantly by lateral loads. So yes, there's gravity loads, and they're still important. They have to be resisted, but it's the resistance to the wind and to the seismic actions that are driving the design of the structure. And then lastly, a mid-rise building is a building where the design of the system is governed by both gravity loads and by lateral loads. Okay, a high rise can also be defined based on fire protection. See, the length of a rescue ladder on a truck is roughly 100 feet when it's extended. If you place the ladder at an angle of 50 to 70 degrees relative to the horizontal, that means that ladder, that truck, can reach about 80 to 90 feet above the ground. Thus, for fire safety, stories above a certain height are required by building codes to have approved sprinkler systems. So this is one definition of what a high-rise is based on fire protection. So the 1997 Uniform Building Code said that any building higher than 75 feet was considered to be a high-rise vehicle, and that brought in other restrictions to the design of the structure. Okay, tall buildings represent challenges in general. First of all, the materials tend to be of a higher strength. You might end up with a higher strength concrete. The columns tend to be larger to resist the extra gravity loads, and the footings and the foundation tend to be larger. Additionally, larger pumps need to be installed in basements of the building to push water to the top. There also needs to be special considerations taken for heat exchangers and air handlers and things of that nature. Not to mention just the logistics of getting people in and out of the building. You need express elevators, you need more elevators, and things of that nature that come in when you're considering buildings that are considered to be tall or structures. Okay, the term skyscraper was coined in the 1880s for buildings that were 20 stories or taller. These started to pop up in Chicago and in Manhattan, and were primarily due to increasing land prices in the cities. So it was cheaper to buy a small parcel of land and build the building higher than it was to buy a larger parcel of land and build the building not so high. So early skyscrapers basically were steel framed interior with masonry facades, but modern skyscrapers use both steel and or concrete for their structure. Slide shows a list of the world's 10 tallest buildings as of May of this year. And I got this off of Wikipedia, so take it for what it's worth, but it's probably pretty good. So the world's tallest building is in Dubai right now. The building has a height of 2,700 feet. So bear in mind that there's 5,280 feet in a mile. So this building is roughly half a mile high. It has 163 floors, and it was completed in 2010. A little bit more about that building. It was completed, it said 2010, this says 2009. The primary structure is made out of reinforced concrete, and it was designed by Skidmore, Owings, and Merrill. The architect was Adrian Smith, and the structural engineer of record was Bill Baker. I've actually met him at some conferences. I don't know if he'd remember me, but I remember him. Contains a total of 57 elevators and 8 escalators in that structure. Okay, the tallest building in the U.S. is the One World Trade Center in New York, New York. It's the 6th tallest building in the world. It's 1,776 feet tall. All right, I think that's a play on our independence, 1776. 104 stories in it. It was completed in 2014. The primary structure is concrete at its core with steel frame outside of that. It was designed by Gordon Gill Architecture with David Childs as the architect, and the structural engineer was the firm WSP Cantor Schnuck. That correctly. And then there's the second tallest building in the U.S. is Central Park Tower in New York, New York. It's still being constructed, but it should be done soon. It's 1,550 feet tall, 98 stories. And I think that the primary structure is concrete, but I couldn't confirm that. So the designer on this is also Gordon Gill Architecture, with Adrian Smith as the architect, and Fazlur Rahman Khan as the structural engineer of record. An interesting factoid about this building is that the owner paid $55 million in air rights so that part of this structure could be cantilevered out over an adjacent building. So they couldn't build it wide enough because of the size of the lot. But once they got to a height that was above the adjacent buildings, they actually expanded the structure outwards and cantilevered it over those additional. And then lastly, this wouldn't be complete without acknowledging the structure formerly known as the Sears Tower, now known as the Willis Tower in Chicago, Illinois. It was the tallest building in the world from 1973 to 1998. It's 1,450 feet tall, and it's primarily a steel building, again designed by Skidmore, Owings, and Merrill. So okay, that concludes this presentation. Here are the references that I used for the material in here. At least I think I got them all. Yeah, hopefully from this you can take away the different types of structure types and the different classifications of buildings. We'll expand upon that in future lectures.